In section 4.4, we're going to learn a very useful technique for evaluating limits. In fact, I alluded to this back when we were in section 2 when we were doing some limits that were not necessarily so easy. This is called L'Hopital's rule. I like to write it this way with the O because that's sort of the way that the French write the word now, even though I guess back in the time of L'Hopital, the Marquis de L'Hopital, he wrote it with an S, so you can write it whichever way you want. It's really not pronounced hospital, even though it looks like hospital. It's L'Hopital because the guy is French. So, and also it turns out that he didn't even come up with this result, by the way. He was a Marquis and he was very interested in math. And at the time he had a lot of money, so he got one of the Bernoulli brothers to basically tell him that if he paid the Bernoulli brother, I think it was Jacob. No, it was John. Okay, so there are a couple Bernoullis that get confused. So in any case, he basically sponsored John Bernoulli for a year and gave him a salary saying that, okay, whatever you come up with in this year, it's going to be my result. So that's how this rule that Bernoulli came up with is now known as L'Hopital's rule. Well, you know. But all right, so we will remember L'Hopital for that. And also, he did write one of the first textbooks on calculus. So it's not like the guy knew nothing, but this is where it is. So what this is it's a rule for evaluating limits of indeterminate forms. Two specific indeterminate forms. We've got 0 over 0 or infinity over infinity. So a lot of the limits that we've seen back in chapter 2 were of this form, right? 0 over 0 or infinity over infinity. And we said, okay, if you've got this indeterminate form, you have to do some work to figure out what's going on. Divide by the highest power, do a bunch of algebra, all that stuff. And for the most part, all of the ones we were talking about back then, you could do that with. We just didn't do the examples where it was very difficult to do that. If you needed to use like a lot of trig identities or whatever, I skipped those. Because once you know this rule, you don't have to worry about doing it that way. Okay? But this rule requires doing derivatives. So this is the way it's set up. If you have a limit, I'm just going to go straight to the end here. Like, if you have a limit of this form, f of x over g of x, and it turns out that if I'm looking at x going to some point A, if you've got either the case 0 over 0 or the case infinity over infinity, the ratio of the two doesn't change when you take the ratio of the derivatives. The limit of the ratio of the derivatives is the same as the limit of the ratio of the original. Okay? So it's kind of weird, but in fact, you can show this for continuous functions pretty easily. And what happens is, now notice we're not taking the derivative of the whole thing, right? If I were to take the derivative of this, I would have to do the quotient rule because it's a quotient. And of course, we know that the limit, if I take the derivative of something, I have the derivative, it's a different function, so the limit's going to change. So the rule is not that you take the derivative of the whole thing, but that you look at this as a quotient and you look at it, say, as a ratio of two different things. And we're going to, when you can't tell which one is going where, which one is going faster or slower or whatever, or where it's going, right? Because we know that if we've got this like 0 over 0 or infinity, it could be going to 0 or infinity or anywhere. So you can't quite tell here, but the derivatives have the same ratio, and oftentimes, though not always, but oftentimes the derivative is a little bit simpler. So maybe if I look at the ratio and the derivatives, I'll be able to get a limit that's not an indeterminate form. Okay, so I'm looking at the derivative of the top function divided by the derivative of the bottom function. Right? This only works if you have an indeterminate form. If it is something where the limit is not 0 over 0 or infinity over infinity, you can't use this trick. You will get the wrong answer. So here, let me do one or two so you see what I'm talking about. My first example. Limit as x goes to 0 of x squared over 1 minus cosine x. So here's my limit. If I put in the 0, obviously I have 0 in the top and 1 minus 1 in the bottom. So this is of the form 0 over 0. It's that indeterminate form. So if I do L'Hopital's rule, what I want to do is I want to take the derivative of the top, which is going to be 2x, and then the derivative of the bottom, the derivative of cosine is negative sine, so this would be sine x. All right, well, that's not great, right? Because I have the same problem, right? If I put in x equals 0, I have 0 in the top and I have 0 in the bottom. But that's okay, because I can do it again. So you can do L'Hopital's rule as many times as you want. So as many times as you need, rather, to get to the result. So if I take the derivative one more time, right, 2x goes to 2, and sine x goes to cosine x, and now when I evaluate this, cosine of 0 is 1, so I have 2 over 1, and my answer is 2. Very nice. Before that, I might have had to do quite a bit of work with this, maybe multiply it by something crazy and see what I can get possibly to get a result out of it. But this gives us a really lovely way of quite quickly getting to a decent answer. Now, of course, it doesn't always work. You can always find an example where L'Hopital's rule doesn't work, so it's not a panacea. But in many cases, you can get a really nice answer. All right, let's look at another one. Okay, that looks kind of cruddy, right? E to the x plus e to the minus x over 2, minus 2 in the top, and e to the x minus 1 in the bottom. If I evaluate, I'm going to get e to the 0 plus e to the 0 minus 2, or e to the 0 minus 1. That's 1 plus 1 minus 2, and 1 minus 1. So yes, this is of the form 0 over 0. So L'Hopital's rule, right? See what we get. So this is going to be e to the x minus e to the minus x, 0. And then this would be e to the x minus 1. I think I still have 0 over 0, right? Because this is going to be 1 minus 1 over 1 minus 1. So this is still 0 over 0. Let's do one more time. See what we get. Am I going to get 2 again? What if I get 2 again? I didn't know that. They don't all turn out to be 2. Sorry. Bad example. Right? It turned out to be 2 again. All right, that's fine. Right, because when I put it in here, now I'm getting 1 plus 1 over 1. So I get 2. All right, but I guarantee they're not all going to be 2. Okay, so I have one more example of a simple sort, but I want to be careful that this example really makes a good point. The point of this example is that L'Hopital's rule only works for these indeterminate forms. So you can't just sort of willy-nilly, whenever you see a fraction, you try to use this, because you will just get the wrong answer. And here's an example. Right? Fine. So let's say I see a fraction and I use L'Hopital's rule. I'm going to get limit as x goes to pi. Derivative of sine is cosine. Derivative of cosine is negative sine. Okay, so now if I put in pi, I get cosine of pi, which is 1, negative 1, but with a minus. So, and then sine of pi is 0, so this looks like it's infinity. Problem is, I skipped the first step, right? I didn't check that this was of that form. So if I put this in immediately, I'm going to get 0 over 1 minus 1, 0 over 2. So this limit is just 0 immediately when I evaluate it. So doing this is wrong. It'll get you the wrong answer because you started from something which wasn't an indeterminate form. So it really has to be, your very first step always has to be to plug in the number and check if it's an indeterminate form or not. And I do believe in the homework they do mix it up. So you do need to check each time.